Let me know if it says that it's recording.
You're good.
Okay. Share screen. Okay, let me know when you guys can see my screen as well.
Yeah.
Okay, great. So we're gonna start off with steering. So Ryan, do you want to just kind of explain the different components? Yeah, the different components, why they're important, what their function is, and
Sure.
you know, like how to manufacture it, like if it's like a CNC or if you're just cutting a tube, you can mention that as well.
Sure. All right. So I guess to start off with steering, the most fundamental part or system, I guess, on the steering subsystem is the rack and pinion. So you have a pinion which turns and meshes against the teeth of your rack, and that in turn turns or moves your rack linearly across an axis. That pinion is connected to a steering column, which is made up of several tubes. In this case, we have 3 tubes connected with 2 single cardan U-joints. They're called single cardan because there's 1 point of movement within the U-joint. And the reason for why we have 2 single cardan U-joints is so that since the rack for this car is off-centered from our center plane, we want it so that the axes of rotation for when the steering column intersects with the pinion and when the steering column intersects with the steering wheel, those axes are similar. And the steering column is connected to a quick disconnect, which in turn is connected to a steering wheel. So yeah, you can see that the steering wheel turns the steering column, which turns the pinion, which turns the steering rack. And the steering rack is also connected to tie rods. For this year, the tie rods are adjustable, which if you want to zoom in, you could see through the threads, which would allow us to adjust steering characteristics of the car. This tie rod is also connected to a steering arm, which is shown in the wheel. So yeah, the tie rod connects to a steering arm, which then connects to a steering bracket, which then connects to an upright, which is basically that big blocky thing you see in the middle of the wheel. So as you turn the rack, you move the, as you turn the steering wheel, you move the rack linearly, which then moves the tie rod, which then moves the wheel. And if you want to take a closer look at the rack, you could see that there are some little blocky bits right next to, I guess, the sides of the rack itself. I guess they're not present here, but if they were not hidden, you could see that those would be like small little circular bits. Those are O-rings. And we call those bump stops because we don't want the rack to move a certain distance too far, I guess, from the center of the rack itself. And we want to do that so that the wheels don't lock, which means instead of having the wheels turn, you're basically pushing the wheels instead against the ground. And we don't want that. That just prevents us from moving entirely. Let's see. So I guess for manufacturing, we don't, well, we were planning on manufacturing the pinion, I believe. But for now, we're reusing old pinions from our steering rack. And the old manufacturer for our rack is no longer a manufacturer because they're out of business. And so we've taken to manufacturing the rack ourselves using the lathe. And to get the teeth made, we send those to off-campus manufacturers to finalize. As for the steering column, we cut the tubes and we purchased the single cardan U-joints. Sorry. Yeah, that's I think basically it. Any questions?
Kind of to clarify a little more, for the rack itself, so something that you guys will learn a little bit later on throughout your classes, or probably already have, but there's a set number of teeth on this rack, and based off of the different characteristics of the gear, the different characteristics per se, like the pitch, stuff of that nature, the rack itself has a ratio of 6.4 to 1. And what that basically means is the amount of times you have to turn the steering wheel to get your tires to turn. So it's a ratio between your steering wheel and your tires itself. So the higher your ratio is, that means that you have to turn your steering wheel more to get your tires to turn 1 degree. The higher that ratio is, the easier it is to turn your steering wheel, which is a good thing, but you also have to remember that the higher the steering wheel is, you're going to be rotating your hands more, and you don't want to do that when you're racing because, first of all, you have wrist restraints on, so you can't really overlap your hands. And also, it's just undesirable. It just takes away from what the driver has to do. The driver has to put in more effort to turn the steering wheel, even though it is easier to turn the steering wheel. So on the other hand, if you have a really low ratio, then it's harder to turn the steering wheel, but you don't have to cross your hands over, and you only have to turn the steering wheel a little to get a lot of wheel rotation. So we chose 6.4 to 1. This was chosen a long time ago, based off of when we used to purchase the rack itself. But the 6.4 to 1 we found was a really nice in-between state of having a high ratio versus a low ratio. So we don't have to turn our steering wheel too much to get our tires to rotate, but at the same time, it's not too hard for the driver to turn the steering wheel. There's also a lot that goes in when it comes to the geometry. So the coordinates, you can't just really place your steering rack and the steering arm in random locations, right? They have to, steering and suspension, as we'll go into detail probably in a different lesson, they are very specific. So there's something called like toe and camber. So toe is basically how far in your tires are going. I can find a picture for you.
1 second. I can pull it up from the manual.
So this kind of shows it. I do things, I'm sorry. Okay, so here, if you guys can kind of see it, when your tires are pointed inwards, then that's called toe in, and if your tires are pointed outwards, then that's called toe out. So based off of where you're putting your components, you're going to get different toe in values and different toe out values, and that changes how your car is going to travel in a straight line and in curves, as well as if you're going over bumps, it will be kind of hard to, let's say you're going over a bump and then your tires want to toe in. Then obviously when you reach the ground, your car is going to want to jut in one direction and make the car unstable. So basically, long story short, we have to place these components in a very specific location, so we get desirable values.
Neha, I don't think we can see whatever you're.
Oh my gosh, I am so sorry.
Yeah, you need to, I think, move out of your browser. Or the current browser you're showing.
Oh my god. Okay.
You're probably only showing SolidWorks right now.
Yeah.
Okay, I have no idea how to do it otherwise.
I could share my screen. I've got the pictures up. You want me to show it to first?
You're allowed to, but I can
Oh, I can't.
put the link in the chat. That works.
Yeah, that works. That'll be easier.
Okay.
Yeah.
I'm sorry, I'm very technologically challenged, so you haven't noticed, but yeah, so if you click on just like the Google link, you can see different pictures of the toe in versus toe out. It's just how your tires are configured, and the components where they are located will affect that as well. So now you guys can see my screen, the SolidWorks screen.
Yeah, we see SolidWorks. Go on.
Yeah.
Okay, great. Yeah, like I said, we'll go over the different geometry points in a later time. But yeah, that actually is kind of all I can think about for steering. Does anyone have any questions? It's not like a very intense subsystem by any means, but it is very, very crucial at that same point. So we do a lot of testing with this. We'll put strain gauges on components like our tie rods to make sure that they won't break. So that will give us a ton of data points on when the component experiences a lot of stress, whether it's going through turns or jumps, or going over logs. So we'll be able to get all the information, see when the tie rod is the closest to breaking and if we need to increase the factor of safety. That is a very big test that we've had to do recently, and actually we're not able to finish because of COVID. But the reason that was so important is because one of our tie rods actually broke during competition in 2019. The bung completely snapped off at this point. So right here, it just completely snapped open. Thankfully, we were on our last lap, so it wasn't completely devastating. We kind of made it through the finish line with like half of a wheel like sticking out. It was kind of crazy, but obviously we don't want that to happen again. So we've had to do testing, and we'll continue testing, hopefully when we're able to go back into the shop. Yeah. Does anyone have any questions?
Wait, so how do you adjust the camber or toe?
Okay, so
Well, I think for the most part, it comes up to the software we use, isn't it? We can really only adjust toe with the adjustable tie rod, not really the camber.
yes, so camber is a suspension characteristic. Basically, you would affect the camber in different ways. It would, hold on, let me post a link of how.
So that's more like suspension, not really steering, right?
Right,
Yeah.
so camber isn't steering, but they go hand in hand. What I've found, because recently we've had to kind of get our, we've had to create new coordinates or location points for our steering and suspension, because obviously we're redesigning the car.
Yeah.
To change the toe, I have found that or the components that will affect the toe, I've found that you will also change the camber. But if your toe is getting better or more desirable, your camber is getting less desirable. So it's a very you get one and not the other. So it's been very hard to kind of find that middle ground. But let me send a link for the camber.
Yeah, I'm not quite sure if this is the question, but there's kind of two components to it. There's the design and there's the implementation component. So as far as the design side goes, at the moment we're using the suspension software Lotus to kind of get all our parameters together, which gives us the parameters which we kind of use to make the CAD as well. But we use to actually jig up the suspension itself when we're attaching it to the car. The way we jig it up is we set it up with the desired parameters we want in terms of particularly caster and camber, such that we weld the tabs that attach the suspension components to the car in the position in which they would achieve the desired suspension parameters, if that makes sense.
Yeah, makes sense.
Yeah, I'll go a little more into detail probably in our next lesson of just explaining more what camber, caster, toe is, and kind of show you the Lotus software that we've been using. I'll show you examples of how changing one component completely throws off everything else.
Wait, so just in general, for something like Baja racing, do you want to have more negative or positive camber?
Nikita.
More negative, I guess, isn't it?
Yeah, it's more.
All right. Okay.
It's better for cornering because I guess as
more
you
grip,
turn,
right?
yeah, exactly.
Okay.
Right, exactly. So going a little more into that is you have negative camber and you're going through a curve, your tires get pushed, and your contact patch is basically what part of your tire is.
Yeah, so that gets bigger, right?
Exactly, yeah. So that's better during corners. So you have a greater contact patch. which is why negative camber is more desirable.
Because I was asking because like I thought it would be like weird because it's like on dirt, not like tarmac. So I like can't imagine like how that changes anything.
Mm-hmm.
So yeah.
Yeah, they're big. Camber is one of the biggest suspension characteristics on my side of things that I personally feel it makes a very big difference, especially in cornering and handling.
Okay, cool. Thanks.
Yeah, you're welcome. All right, is that it for steering? Does anyone have any questions? I can't really see the chat. If anyone does, who doesn't? But if not, we can go on to suspension. All right, okay, let's do suspension then. So Nikita, do you want to?
Yes. So the suspension system of the vehicle, or the suspension subsystem to be particular, is responsible for the mitigation of all the forces that the vehicle experiences while it is in transit, as well as allowing for the delivery of the power to the wheels from the powertrain of the vehicle. So in the front, what we have what is called a short long arm suspension, such that there's two control arms in the suspension, wherein the lower control arm is longer than the upper control arm. So generally how it is made is that we notch tubes in the shape that they are in the suspension components for the control arms, and then we jig them up and we weld them. So as you can see, I think it's fairly self-explanatory. There is a upper control arm to which the shock itself is mounted to, and the chassis mounted of the shock, and the lower control arm to which the so then both control arms are attached to the upright, which contains the hub of the vehicle. On the upright, there's also mounted the steering fork, which connects the steering rack to the upright, enabling for steering input to be delivered to the upright to change the position while it is in transit.
Wait,
You
hold
can
on.
see.
Can you pause for 1 second? Does anyone know how to change this from not being black anymore so we can actually see it properly?
I think it's a render thing. The more components you have, the less. I guess the more the computer has to allocate for rendering until there's a limit or a limit's
Nah,
reached.
I feel like some of us have just changed it all to be the same color.
Okay, all right.
Weird, because I thought it was different colors before, like recently, but I could be wrong.
You sure
It's
they didn't
important.
just change the material?
That's possible, but I don't think
It
that's the
wouldn't be the
case. There are
material
different
because the
materials.
shocks are black.
Right.
So,
I think it's just rendering, honestly.
all right.
Nah, I think someone's changed the
Yeah, I
color.
think someone
We can
changed
argue
it.
about that
Really?
later.
It's fine.
All right,
Yeah,
all
so
right. Yeah,
this
so-
part is the upright. I don't know if you guys can see it, but this whole thing. Okay. You can continue.
So as you can see, the upright allows for interface of all these components. So you have the attachment point for the brake caliper, and then you also have the brake rotor, which is attached to the hub, which is attached to the upright. Between the hub and the upright, you have multiple bearings to allow for the hub to spin and to allow for power to be delivered into the hub by the CV axle. And on the hub itself is mounted the wheel and the tire, respectively.
Wait.
So as you can see, this is the hub. You can have the that part sticking out as where the CV axle goes into. This particular interface between the axle and the hub is called splines, but that's a whole other discussion. So the axle goes in there, and then you have the holes on the inner end of the hub to which the brake rotor is mounted to, and on the outside you have the holes for the mounting of the wheel itself. So this right here is the upright. As you can see, you have the points on the top and the bottom to which the control arms are attached to by means of the ball joint. I'm not sure if y'all have experience in automotive, but it's a fairly common component. And then you have the area in the center for the mounting of the bearings on which the hub is mounted, such that the hub can spin. And you have the holes on either side of the upright to allow for interface between the brakes and the steering to the suspension, such that you have the brake caliper attaching on one side of the upright and the steering fork on the other side of the upright.
Yes, so the brake caliper and brakes on B, this is currently Rev A, so things are going to be switched for Rev B, but you can see that that is on one side of the upright, which is this thing, and then you have the steering arm on the other side, which is attached by the steering bracket to the upright. Yeah, okay. Do you want to talk about the shocks now? And then we can go to the rear.
Yes, so the shock absorber itself is a component that absorbs the shock that the vehicle experiences while it is traversing the terrain. You can see is attached to the upper control arm as well as the chassis. So when the wheels go up and down, the forces that the vehicle experiences are mitigated by the shock absorber component. I'm not sure if it's worth it to go into specifics, but this particular shock absorber has 3 different chambers in it to allow for a variable rate of the motion of the whole suspension.
Yep, and we currently use air shocks. There are different types of shocks. So there's coil shocks, air shocks. One is cheaper than the other. We're going to be looking into if we need to have air shocks or if we can have coil shocks. That's probably something that's going to happen when we get back into the shop, because we need some like serial numbers and stuff like that for our current shocks to try and figure out a good comparison for other shocks. But currently we use air shocks.
This is semantics, but I do not believe what we currently have is 100% constitutable as an air shock, because I believe I think one of the chambers in the shock is nitrogen only, and the other maybe some other like different fluid, but as semantics.
Not a coil shock, something
No.
that involves gases of some sort.
So I'm assuming coil shocks are cheaper.
Yes, they are. Definitely depends on the manufacturer, but a lot of teams run coil shocks. There are certain teams that run, we're going to call them air shocks, but there are certain teams that run air shocks, but a lot of them run coil shocks. I will also send a picture of this in the chat. All right, do you want to move on to the rear?
Yeah, so in the rear, you have the suspension that is known as a multi-link system. So you have the trailing arm as well as the lateral links, which connect the upright to the chassis of the vehicle. As you can see, you have a variety of different connection methodologies on either end. So we shall start with the lateral links, which have bungs on either side, which are welded to a tube. And on each of the bungs, there is a spherical joint that allows for a constrained motion of the lateral link. So then you have the trailing arm, to which is attached the shock. So this is the component that kind of experiences the most force and mitigation of the forces experienced by the vehicle. So its motion is a little bit more constrained than the lateral links to help it absorb the forces resulting from the motion of the vehicle. You can see it consists of
I'm sorry, do you want me to turn somewhere? I don't really know where.
No, I'm just like thinking how to explain.
Oh, okay.
So you have the trailing arm upright connector, which connects the trailing arm to the upright, as well as you have the bung on the other side of the trailing arm. These components are welded together and the tube itself is notched so that it will fit the machine components on either end. So the I apologize, but how far into detail should I go in terms of manufacturing techniques?
I mean, you can talk about as much as you want to.
I see. So with the upright, you have a similar situation where it needs to allow for the passage of the CV axle into the hub to deliver the power to the wheels of the vehicle.
As you can see, the upright in the rear is different from what it is in the front.
Yeah.
Just based on the different components that it has to attach to and stuff like that. Also, if you guys don't know what notched is, it's this curved feature over here. It's basically you're taking away material from a tube or a component so it can properly interface on something else. So here we have well, Sam could definitely go more into that if you wanted to, but here we have more of like a curved notch over here so that can attach to the rear upright. It can fit the contour, of this bracket over here, the connector. So it can interface properly and you can do a weld for it.
Yeah. As far as manufacturing techniques go, quite a variety are employed. So for example, for the connector, we use EDM machining. I'm not sure if you've heard of that before, but effectively it's a very hot wire used to cut contours out of metal. So we would then cut the contour of the upright connector out and then perform additional machining operations. And for the hubs and uprights, for example, both in the front and the rear, they're really quite complicated parts that require usage of both the EDM machining as well as CNC machining, not to mention any possible additional operations.
And also currently the rear hubs are also different from the front hubs. But we are working to see if we can make them uniform, which will be really good for manufacturing because then the CNC can just cut core of the same thing instead of having to be set up for different operations. Yeah. Is there anything else for suspension that you can think of component-wise?
I feel like that's just about the basics of it.
Yeah. Does anyone have any questions on suspension? If you want me to zoom into something, or I don't know, anything.
So how come you guys use air shocks instead of coil?
So that was something that was decided by earlier teams. They decided to go forward and buy these shocks. However, these shocks were very expensive. One of the reasons why they wanted to get shocks like this is because, like Nikita said, it is adjustable. You can tune it based off the different chambers. So you can get more desired characteristics if you know how to tune them. But what I've heard from previous years is that they don't really use that tuning aspect, which is a very big feature for these current shocks, which is kind of why we're trying to see if there's other shocks that we can get, because we're paying so much for these and we're not really using them to their full advantage. But there are 3 different chambers which control different components of the shock. And yeah, that's why a lot of people run air shocks.
Yeah, I believe part of the reasoning is also that conventional spring-based shock absorbers would only allow for a set spring rate, if that makes sense. Whereas what we're using allows for a variable spring rate and then wheel rate, respectively.
Yeah.
So it's
Yep, so there's a lot of manufacturing that goes on in this subsystem. There are some things that we send out to get, but very, very few. Like we purchase the shocks, but most of the stuff in this subsystem are made, whether it be on the lathe or some type of mill, whether it be the CNC or a hand mill, and then the EDM as well. And there's a lot of welding that goes on.
I got a question.
Sure.
Why do we use different types of suspension between the back and the front?
Yeah.
So this is a interesting question. So I think the best way to address it is the historical context, because for a long while, what we had running was a rear-wheel drive-based vehicle, such that only the rear wheels were powered. Now we're switching up the design, so when we actually get to building this design that you see at the moment, if we ever get to building it, but that's another discussion, we're going to have a four-wheel drive design such that all four wheels will be able to be powered. So in the context of the two-wheel drive design where the rear wheels were powered, as the rear wheels only need the delivery of the power to them and didn't require interface from steering or from brakes, because the brake rotors were inboard of the vehicle such that they were where the CV axles came directly out of the gearbox, then you had the brake rotors. So you don't have the requirement for any of the additional interface components on the suspension upright component. So you'd be able to use this type of multi-link system in the rear of the vehicle. Whereas in the front, even in our previous design iteration, we had that requirement, and we still have that requirement, such as to allow interface between the brake system and the steering system at the upright of the vehicle, which is more easily done with the short, long arm design. Because as you can see in the rear, based on this suspension system, you can't really rotate the tires, so you can't have any steering input. So we don't need that. So we can use this type of design, and we don't need any of the other additional interfaces which are necessary in the front. Because you can see with the ball joints that connect the upper control arm and the lower control arm to the upright, that joint is such that it allows for steering input to be delivered to the wheels so that the wheels can turn and the vehicle can turn respectively. Not sure if that addresses the question enough, but
No, that does. Thank you.
All right. Does anyone have anything else before we move on to brakes?
Wait, so you're certain that air suspension gives you better performance than like coil?
So
We are
it's
not-
not. Yeah, no, you can continue.
I mean, obviously nothing is for certain, but based on what we understand at the moment, we are fairly confident that it allows for better results to be obtained.
Right. So that's also, it's not necessarily that you're going to get better performance.
It's the tuning that's important
tuning.
too. Yeah.
Exactly. Yeah.
Okay.
So if you know how to use it, then for sure, like you can run different tests to figure out what parameters you need. But right now we don't have I don't even think we have the testing to figure out what parameters specifically we need and how to specifically tune the different chambers.
Yeah.
But yeah.
Yeah, it's important. Okay, thank you.
Yeah.
I've got a question.
Yep.
Are I can't see from this angle really, but are the shocks directed relative to the front plane of the car? Is it like a directed upwards thing? Like, is there any forwards or backwards angle to the shocks? I see that. Okay. And what decides what angle forward or backwards the shocks are at?
I mean, it's a number of factors. So I think you could first consider the kind of force distribution situation, because obviously different angles and different mounting positions, we have different force distributions. So some may be more desirable than others. Another element of it is actual modeling of it, if that makes sense. Because part of our intention with this design was to preserve the kinematic properties of the previous design while allowing for the passage of power delivery to the front wheels, which we must do now. So the shocks are relatively similar configuration to that of the past design to try to preserve some of the properties of that design in this particular design.
And also, so for shocks, so we already bought these shocks that are shown here, which are the air shocks. So we bought them for the last competition, which obviously did not happen. And when you buy a shock, you have to buy them to a specific length per se. So you can't, so there's only so many configurations that you can do with one length. You can have it at different angles, but like Nikita said, if you have it at different angles, then the force distribution is going to be different. You're going to have different handling characteristics because certain forces are not going to be going through the shock like that. So because we had this current shock, we knew that it would have to be kind of at this angle. We wanted to preserve what we had in our rear-wheel drive car because, you know, you don't want to change all of your variables at once because you're not going to know what is wrong and what is right. And because we kind of knew that this was something that would work, having it at such of an angle, we were kind of just like, okay, we'll kind of keep it this way, and then if we need to change it, we can.
Thank you.
Okay. Janet, do you want to explain the brakes?
Yeah, sure. Okay. Well, we can kind of break the brake system into like three parts, right? Three main components. And then we'll add more components as we kind of travel through the concept, right? So let's focus on a master cylinder, brake lines, and calipers. So when you're driving like down the street, right? You go at a certain speed, then you decide to, your foot presses down on the brake pedal, you exert an amount of force, and then after a couple of seconds, you stop, ideally, right? But your foot, like the force that you exert from your foot onto the braking pedal is not enough, right, as a human to kind of stop the car. So what happens? Well, the braking system multiplies the force that you exert, and that's what causes the car to stop. So if we take it from the top, from the master cylinders, on the top, there should be a reservoir, which is like a little tank. And the purpose of this reservoir is just to hold in fluid. The fluid in this case is braking fluid. And like a lot of fluids out there, it's non-compressible. And this is very important. And we'll talk a bit more about it. But the reason I bring this up is because you don't want any air to be in the brake lines, because that would just really mess up the whole entire braking system. So great, you're driving, you step on the brake pedal, you have the fluid from the reservoir travel down to the master cylinder. In the master cylinder, if you were to like break it, if you were to like see what was inside of the master cylinder, you would find a spring, you would find a little piston and a push rod. All of this, right? And you would also have like brake lines connected to the master cylinders. Now the brake lines lead to the calipers in the front and the calipers to the rear. Again, we're gonna have to use a little bit of imagination because the brake lines are in here, but the brake lines are basically like thin little tubes. They're flexible, they could be of plastic, they could be of steel. At least that's the brake lines that we use in this Baja car. So the fluid from the reservoir travels from the master cylinder to the brake lines to the calipers, and calipers are just like a holder of sorts, right? A holder that has two pistons. It could have one piston, but we use two pistons. And when we exert that force, the fluid like pushes out the pistons. Inside the caliper are brake pads. And in between all of this is the brake rotor. So we combine everything that we just kind of talked about of you driving the car, press the brakes, the fluid from the top of the reservoir travels from the master cylinder to the brake lines, to the calipers. The calipers then, from that pressure, the pistons exert out compressing the pads, compressing the rotor, and causing the car to stop. So that's basically what it is. In the beginning, I did mention that, you know,
Wait,
the
hold on,
force
sorry.
that you exert.
Yeah, sorry, just because I have like it open now.
Oh,
Want to like, so like basically like the brake pads are in here, and then like
yeah.
this is the master cylinder, just so you guys can see it a little better. I mean, not master cylinder, sorry, the brake caliper. And then this is the brake rotor, and then inside of this you have the brake pads inside. There's two of them, so they like contract obviously to stop the brake rotor from, brake rotor from rotating.
And if like you see like those circles, like more or less that's where the pistons are. So that's where everything kind of contracts and stops the rotor from spinning. Because when it, you know, when the car when you're driving the car, the rotor spins, and when you want it to stop, you kind of need that friction to stop the rotor from spinning, and you know, thus the car stops. So just to kind of go back again of how roughly the force multiplies, what I mentioned in the very beginning, I can give an example, and if it doesn't work out, then I guess we can pull up some pictures. But if we imagine like how it's the idea that I want to throw out there is that like if you the increase of force is directly proportional to the decrease in distance. And to kind of drive this point home, if you imagine a seesaw, right? And you have the midpoint, well, you have two little kids kind of going on of similar weight to the seesaw. So ideally, you know, it's kind of balanced, right? If you were to move the midpoint to the left or to the right side, where there's like a 75-25 brake, now and this is independently, right? If one kid of the same weight goes on the 75% of the seesaw, right? The seesaw will move at a certain amount. But if that same kid, same weight, goes on the 25%, that's free of the seesaw, the force, like there's a lot more force being produced on the short side, and that's just kind of the way it works. The way that your foot force is multiplied in the way the braking system multiplies your foot force kind of to the pivot point, and then the distance from the pivot point to the piston head. I'm seeing that like my connection is unstable. Do you guys
it was
still
just,
hear
can
me
you
well?
repeat that last line that you said about the piston head?
Oh, okay, yeah. So in the system, it's the same concept as the seesaw, right? So it's the distance from the brake pedal to the pivot, and the pivot to the piston head. The master cylinder does have something to do with how we exert force, but basically the majority of the time, the distance of the pedal brake to the pivot is 4 times the distance from the pivot to the piston head, which is why when you exert that, your foot exerts that force to brake, more or less, you know, the braking system exerts the force 4 times the amount that you did. And again, like okay, you know what, just stay there in the caliper and the master cylinder, because the master cylinder does play a big part of it, depending on like the on the input of the cylinder, so the circumference of everything that also plays with it. So everything is the whole system kind of does its part to make sure that it has your back in a way, like that the car flying where you're exerting to stop the car. I don't know if that made any sense to you guys, but that's the way
So we currently
I feel like I could best explain it. But yeah,
what is our brake bias that we currently have?
I'm sorry?
The brake bias that we currently have?
Oh, the bias bar?
Yes.
Like how much is in the front and how much is in the back? Oh,
yes.
Yeah. So currently I think it's 60-40, with 60 being in the front and 40 being in the back. But we always kind of just like move it around just because we do want the wheels to lock. And that's always kind of been our problem. So the bias bar.
Yeah. Okay. I was just
All
gonna
right.
ask
So
that.
so the bias bar basically distributes, well, yeah, it kind of distributes braking force. So we design it great, and it should work. But sometimes we do need that bias bar to kind of balance the force, or at least the torque that the front receives in comparison to the back. We also have a proportioning valve, which I think the car has. It should be like on the right side if you look at it from the top view. But I'm not sure if it does. Oh, it doesn't. No, no, it doesn't. Oh man. Well, we also have a prop valve, which is does kind of the same thing. It just directs more, it's just more focused towards the rear brakes. And the reason why we first implemented these two things was because we did have a lot of problems when we went to competition. Um, there's a component, we have to do a whole bunch of tests, right? Acceleration test, braking test. And in the braking test, you drive, you brake at a certain point that they indicate, and your wheels have to lock, right? And if you don't pass that, then you can't really go to the endurance part of the race. So we've had like a lot of problems where our wheels, our rear wheels, and sometimes our front wouldn't lock, which is why it's nice on the day of, which is not, well, actually it's not nice of the day of, but it's convenient to have on the day of, since we didn't really do our system, we didn't really create the system all too well, to kind of calibrate it there and to play around with it to see if we can kind of have those adjustments. But yeah, we do have to put in a bit more work to really understand and research how we can go to competition without having the need to like toy around with the braking um balance too much. But yeah, that's what it is. I don't know if that was your question, Neha.
Yes, that explained it. Well, thank
Okay, cool. Yeah, and that's it.
you. Yeah. So a lot of
I
brakes
forgot
is
one thing.
not.
I'm sorry, I forgot one thing. So about what we manufacture, we don't really manufacture or fabricate. I'm sorry, we don't really fabricate a lot of things in-house for brakes. We either, the majority of the things are bought, or we have one of our sponsors to kind of help us out, and they, you know, manufacture it over there. The things that we manufacture in-house would be like the caliper mounts, the master cylinder mounts, any spacers that we need, like obviously the tubes and like the master cylinder tube that's highlighted right there. Like all of those things are manufactured in-house. We're trying to manufacture the bias bar. Well, I guess design, because we can't really manufacture it now, but you know, it's not this subsystem, we don't really manufacture a lot. It's a lot of the things are store-bought, or you know, our sponsors kind of help us out with that. So yeah, the end.
Does anyone have any questions on brakes? So for the all-wheel drive car, something that we've had to work with for brakes was trying to figure out where we're going to place the brake pedal. So we have like the, well, obviously like depending on the length of your brake pedal, you're going to have a specific, like, if you took Mech 101, you'll know what I'm saying. I just can't really explain it right now, but you have like a, do you know what I'm talking about, Janet? Like the amplification, like if you like it's a mechanical
Right.
lever. Do you know what I'm talking about?
Yes. So like basically, the problem that we have yeah, there you go. Thank you. Moments.
Yes, there we go.
The problem that we had is that the original setup of our brakes, the brake pedal was a lot lower, right? But the reason that we're lifting it up is because, well, we have so many things in the front because of the all-wheel drive system, that if we were to leave the pedal where it was, when you go and press the pedal, like you would bump into a lot of things. It would just not be convenient. It would be really, really weird. So we kind of have to lift that up. And thankfully we didn't really change the size of our length of the pedal, because if we did do that, then that would again kind of mess up our original braking system, because of the moments that Ryan mentioned, and how the length is proportional to that, proportional to like the force that we exerted, similar to the example of the seesaw, right? But we just kind of lifted it up as a way to not mess with any of that work. Yeah.
Yeah, that's what I was trying to explain. I just couldn't, I don't have words for that right now. Yes, there's that. For all-wheel drive, there's inboard versus outboard brakes. Do you want to, like, in the front of the car, we have outboard brakes, which means that the brake rotors over here are on the outside. They're located inside the tires, but basically in the rear, which you can't see here, the brake rotors are on the chassis itself or inside the chassis. So for our all-wheel drive car, we're trying to see if in the front we can also have inboard brakes. So we can push the brake rotors from being out here to inside as well. It's just a lot of it has to do with packaging. The reason we had, a lot of it has to do with packaging. It also depends on where you want to stop the transfer of motion. But I don't know, is there anything else you want to explain about inboard versus outboard brakes, or like the pros versus cons of having one versus the other, why we have inboard in the rear?
Well, Nate had really explained it really well. Like, if we want to break it down in a way that we can like really explain it, it's like outboard brakes, the brakes are outside of the car. Inboard brakes, the brakes are inside of the car. Visually, right? Visually. You can always have the debate that like outboard brakes, you run the risk of it, of all the components that we mentioned getting dirty, of things getting inside the rotor and stuff like that, and like that overall just negatively impacts our braking system. And there is a debate and a point that you can make of that. But a lot of the times, as Nate has said, like it's more compact to have it in. It's just what kind of is best for your car and like the placement of the brakes. Because if you have it on the outside, then you can say, oh, well, if I would need to take something out, then it's a bit easier because it's on the outside if you position it in a way that's flattering, versus the inside if you position it in a way that it's a bit more harder to get in with all your tools, then it kind of becomes a pain. So it just really does depend on what you want for your car, what kind of what better suits your needs in terms of packaging. Because there are like positives and negatives, but those positives and negatives in the long run don't really contribute to major braking loss or major braking gain.
Yep.
I've got a question more on the braking systems overall. Does the way the brakes work impact the way that the tires are chosen?
The tires are actually chosen as a suspension. That falls under suspension. So,
like tire treads, I mean.
Yeah, that's suspension, I think.
Yeah, I don't really think in the past there has been a correlation between both of them. I could be wrong, actually. That's a pretty good question. But all I know is that suspension is responsible for choosing the tires. As you can see in the rear, we currently have different tires than in the front. That has to do mainly with, that was chosen for driver preference, actually. Like, our driver can be like, oh, I want like bigger tires in the front versus in the rear.
I think the main difference would, I guess what you're looking more for is rotor sizes, because what's I guess being affected more so than the wheels is the rotor. The bigger the rotor, the easier it is to brake, I think.
I mean, not really, but that's, I guess, also answers the question. So, yeah. I mean, like, does braking like think about how the car actually interacts with the ground or not?
I mean, that's how we slow down, right?
Yeah, but like it seems like the brake subsystems is focused more on the internal components that stop the tires and not necessarily the car.
So, yes and no.
I mean, yeah.
they are like yes, like even though brakes doesn't directly interface with tires are chosen and that aspect, at the same time we do have to tune the cars so whatever tires and stuff we do choose do like stop the car. That's not a really good answer to your question.
Actually, it was kind of pretty good.
Oh, okay.
Yeah. Thanks.
Yeah. Yep.
Wait, so our caliper size is gonna be fixed, but we can change the size of the rotor?
You can change the size of your calipers as well. That's actually something that that Max and another member, Jonathan, are currently working on. If they want to explain more, they totally can, because I know Max is here. But basically, you can change your brake caliper size. Currently, our calipers, they are rated for a lot more than what our car actually experiences. So if you have smaller calipers, Max, you can explain this a lot better than me. If you want to unmute yourself. Max.
Sorry. Yes?
Yeah, no, they're just asking, can you like explain like the caliper and rotor calculations that you're currently doing right now?
Oh, so currently we are checking to see how much, basically how much pressure has to go into the lines, and how much that pressure corresponds to the force applied by the piston inside the caliper, to see if the current calipers we have are overkill or not. Because if they are overkill, then we can probably find smaller calipers, meaning that they're more compact, especially in our front, because our front has just so many components in them between steering, brakes, and suspension, and powertrain, because there's a differential in the front. That means the packaging is very, very tight in the front. So if we could find a way to, well, first of all, this entire thing is we are trying to bring the outboard brakes, so having the calipers on basically on the hubs, to what we have in the rear, which is basically called inboard brakes, where it would be much closer to in the front, it would be the differential. And so to do that, we need to have a more compact packaging for this caliper rotor combo. And so basically, me and Jonathan are going through calculations to see if we can reduce the size of, well, first of all, just reduce the size of the rotor, because right now our rotors are about like 7¼ inches in diameter, and we'll see if we reduce that size to about like 6½ inches, if we are still able to generate enough force inside the calipers to lock up our wheels. It's basically an overview of what we're doing.
Yeah, so basically you can change your caliper size and you can change your brake rotor size. It's kind of about finding like the perfect fit for both of them.
Yeah, that's with everything, right? Like the perfect fit.
Yeah, exactly. Yeah. Does anyone have any other questions about brakes?
This is a really bad question, but where's the engine? Where do you put it? Is it in the front or like the middle or something like that?
So our engine is in the rear.
Oh, okay.
Yeah, but we have a differential in the rear as well as a differential in the front, which isn't really seen here. And that is how we get the transfer of power, as well as we will be having a drive shaft that will go from the rear as well.
So now you're saying you have a diff in the front and a drive shaft. So was it like rear wheel drive or something at one point?
Yes, so the other years before this, we've had rear wheel drive cars. So that is actually why we're doing a ton of revisions.
That's interesting.
Yeah, so now it's all-wheel drive. There's a lot of testing that needs to go in because of that. Yeah, everything about the car is basically changing.
Oh, it's gonna be better, hopefully, though.
Hopefully. Hopefully. But yeah, so to just quickly like say like what we're kind of going to be doing for this new revision of the car. We're going to be working on suspension characteristics as well as steering characteristics, manufacturing the bias bar, like what Janet had said, working on unifying the hubs, doing brake calculations, changing our steering arm, finding different steering wheels so we can help with the ergonomics and driver comfort. Another very big thing that we're going to be doing is doing FEA on all of our components. So you guys will be taught how to do FEA, which is structural analysis, making sure that all the stresses are proper, and that we have enough factor of safety. That's kind of just like a very general overview of what we plan on doing for vehicle dynamics this semester. But yeah, I know I went a little over. I said that this would probably be over at like 2, but does anyone have any final questions? There will probably be a steering and suspension handling characteristic lesson at some point next week, to go kind of more into like toe, camber, and stuff like that. So, yeah.
Cool.
I can probably stop sharing my screen. But yeah, anyone have any final questions on anything?
Are we going to end up choosing a subsystem?
So I'm actually still deciding on that. That's something I kind of want your guys' input on. I don't know if you guys would be interested in kind of working more with a specific subsystem. Obviously, if you do choose to work with a specific subsystem, you can change to any subsystem you want. That's one option. Or you guys can just kind of be a general VD member, and whatever subsystem needs help, you can kind of help them with that. In the past, we've done it so people will go into specific subsystems, but it's all up to preference. If you guys want to know a lot about one specific subsystem, or if you want to just know about all of them and then just help whichever one needs help.
Yeah, of note, even if you do pick subsystems, you can always work with another one. Like there's no limit to who you can work with.
Yeah, so it's whatever you guys prefer, honestly.
Yeah, I feel like I need to learn some stuff though, and then like.
Yeah, of course. It's not like you guys are gonna just be completely like thrown into the deep end and have to like work on a complete subsystem by itself. It's just like if you have a specific interest in a subsystem, you can work more with them. But you can talk to any of the subsystems, and we can all like set up different meeting times if we need to just learn more about different subsystems or something that you're interested in. It's whatever you prefer. But I guess we can kind of talk more about that later on if you guys like start to learn more about subsystems and see what you guys prefer. It's not something that we have to decide right away or anything. Yeah. Does anyone have anything else that they would like to ask?
One last thing.
Yep.
Are we going to be using Zoom, or are we going to be using Discord for future meetings?
So the only reason why I'm doing Zoom is because I wanted to record it in case anyone couldn't come. I normally don't record meetings or anything like that. It's very weird to me, because there's usually like minutes that people can read up on. So we usually use Discord. If we do have a lesson, we'll be using Zoom, but if not, if it's like just a normal weekly BD meeting, we will be using Discord.
Okay.
You have
Thank you.
sent Nicholas your Discord information?
I'm in it already, but thank you.
Okay, yep. Yeah, I don't really know where this is going to be posted, but I will let you guys know when it is. And
it will probably be posted on our YouTube channel.
Yeah,
oh my God,
send
we should get.
Send it to one of us. Send it to me or Red.
Okay, we're gonna get so many views. We're gonna become YouTube famous, and it's gonna be amazing.
Yeah, okay.
Yeah. Any last questions? Are we ready to skedaddle? All right then. I hope you have a great rest of your day. And if you have any other questions, feel free to let me know or anyone else know, and I'll let you guys know on future lessons. But yeah, thank you everyone for coming. Bye.
Thanks so much. Enjoy.
Yep.